How we doing? My name is Justin Roe,
And I'm Brian Cobus.
and today we're going to talk about an ANSYS transient structural analysis of a simplified bat and baseball impact. We're going to be talking about a simplified model that we made of a baseball bat impact. We're looking to observe force convergence curves and material responses based on our unique models. And we're also looking to observe physical deformation and equivalent stress maps of the simulations on impact.
We ran our test on 4 different models. Each of the models used a soft polymer ball with a Young's modulus of about 10,000 pascals. In each of those models, we varied the Young's modulus on the material of the bat in order to make it stiffer and see how that affected the results. The first model we used was the same material as the soft polymer bat with a Young's modulus of 10,000 pascals. The second model used a Young's modulus of 500,000 pascals. The third model used a Young's modulus of 1 million pascals, and the fourth model used a Young's modulus of 7.1 e to the 10th pascals. And the speed of the ball was half a meter per second in all 4 cases.
This slide just goes over some material properties that we used for the models. You can see the soft polymer, the medium stiffness polymer, high stiffness polymer all have the same density and Poisson's ratio. The only thing that changes is the Young's modulus. The aluminum has a larger density and a larger Young's modulus than the 3 previous polymer samples, but a smaller Poisson's ratio.
For each of our conditions, we created 2 ANSYS simulations, one that shows the total deflection of the bar and one that shows the total stress within the bar. The first set of simulations we have here is for the soft polymer bat in condition 1. As you can see, the Young's modulus being very low causes the bat to flex quite a bit when struck by the ball. After the models finished processing, you can see that the max stress within the soft polymer bat was 59 psi and the max deflection at the tip of the bat was 4.72 inches. Below you can see a plot of the force convergence that ANSYS processes in order to reach a solution in these models. As you can see, it starts very sporadically, and as it progresses through its solution, it starts to condense and reach really close to that forced criterion.
The 2 plots that you're seeing right now are the deformation and equivalent stress plots or simulations of the medium stiffness polymer. You can see that they do deform a little bit less and the stress is a little bit more concentrated at that fixed base. Here you can see that the max stress we found in the simulation was a bit higher than the last simulation at 5 psi. The max deflection was a bit lower because the stiffness increased at about 2.97 inches. And the plot below illustrates fluctuation. That brief pause is when the bat leaves the ball, and eventually it does reach a solution once the ball hits the bat again at the very end.
Here we have condition 3 with the high stiffness polymer bat, and as you can see, the increased stiffness causes a slightly smaller deflection, which actually causes the bat to make contact with the ball again and get pushed back slightly further, which actually increases the stress a little bit more at the end. The final max stress within the bat was 7.83 psi, and the final deflection was 2.41 inches. Both of those occurred after the second contact with the ball, which skews the results a little bit. And looking at the force convergence plot, again, you can see when the ball separates from the bat, the graph levels out for an extended period, and then when it makes contact again, it once again gets a little more sporadic before leaving the bat again and once again going flat.
Finally, we have condition 4 with the aluminum bat. You can see there's about 0 deflection in the aluminum bat, and as you'll see on the next slide, the max deflection is a result of the ball, which is the only part of this that actually deflects. Although the bat doesn't deflect at all, there is a large amount of stress that is generated. Here we can see what I was just saying. The maximum stress, the highest stress we've had thus far, is 40.9 psi. That's a result of the beam being stiff. The 0.49 deflection, as noted right next to it, is a result of the ball deflecting, not the beam. Although we were throwing some curveballs, we were able to come up with some conclusions regarding the simulations. Like increasing the modulus of the beam increases the stress and decreases deflection. The impulse generated by the ball is not necessarily a linear response. And the stress concentration almost always occurs at the end of the beam. Here we have listed some references. We wanted to thank you very much and ask if you had any questions.